Hello everyone. In today's session, let us learn about a queuing model 2, where we learned about the introduction of a queuing model and model 1 in the previous video. Okay, so queuing model 2 is nothing but single server model with finite system capacity. What about the first model is single server model with uh, infinite system capacity. Before going into deep, let us give the idea about the terminologies. So MM1 is nothing but a single server Markovian arrival and exponential service. So single server will follow this as one. And finite capacity is nothing but k customers is allowed in the system at any time. And the discipline followed is first in, first out service. And we denote the arrival rate by lambda, which follows a Poisson distribution. And we denote a service rate by mu, which follows exponential distribution. And the traffic intensity is denoted by rho is equal to lambda by mu. Come to the next. Let me give the key formulas which is involved in this model, where P naught is defined as a probability of the system is empty. Okay, where that means there is no customer in the system. So there are two categories to define with a P naught. When my arrival rate and service rate are not equal, when my P naught is 1 minus lambda by mu upon 1 minus lambda by mu, the whole power of k plus 1. And when the service rate and arrival rate are equal, P naught is just 1 by k plus 1. So this is for your system is empty. Suppose the probability, we have to find the probability where it exceeds with the n customers. So in the system, then again this two category when lambda is not equal to mu, Pn is lambda by mu the whole power n into P naught. And when lambda is equal to mu, lambda is nothing but that your arrival rate is equal to service rate, then Pn is equal to 1 by k plus 1. Coming to the next key formulas. So lambda dash is defined as the effective arrival rate, where actually it will be like the actual rate of entering the system. So it is defined as lambda dash is equal to mu 1 minus p naught. And ls is will be also with the two categories like as we defined earlier, lambda not equal to mu and lambda equal to mu. So when lambda is not equal to mu, it is lambda by mu minus lambda minus k plus 1 the whole power lambda by mu power of k plus 1 upon 1 minus lambda by mu whole power k plus 1. And if lambda is equal to mu, ls is nothing but k by 2. And lq. LQ is nothing but the average numbers in the queue. That's the number of customers in the queue. So waiting, that is where those are waiting, not being serviced. So it is LQ in terms of LS is nothing but LS minus lambda dash by mu. Lambda dash is effective arrival rate. And next thing is the average waiting time in the system and average waiting time in the queue. It is denoted by W. S and WQ. Actually, W is for the denotation of waiting time. W waiting. Okay. So waiting time in the system is defined as LS upon lambda dash, and waiting in the queue is defined as WQ is equal to LQ by lambda dash. Actually, it has been defined based on your LS and LQ because the formula to calculate your LS itself is lengthy, and if you want to go directly the formula, you have to make use of this one upon with your lambda dash formula. So it's better you can use this little formula concepts like WS is nothing but LS by lambda dash and WQ is equal to LQ by lambda dash. Okay. So let me go with the problem 1. So where patients arrives at a clinic according to Poisson distribution at a rate of 60 patients per hour. Okay. And the waiting time does not accommodate more than 14 patients. So investigation time per patient is exponential with the mean rate of 40 per hour. So we are supposed to calculate, determine the effective arrival rate at the clinic. And next one, what is the probability that arrival patients will not wait? Come to the next, what is the expected waiting time until a patient is discharged from the clinic. So it is very clear, determine the effective arrival rate of a clinic. So effective rate of arrival clinic is nothing but they are asking you to calculate your lambda dash. And what is the probability that an arriving patient will not wait? Will not wait in the sense that if the system is empty, so we are supposed to find here P naught. Okay, and coming to the next, what has happened? What is expected to waiting expected waiting time until the patient is discharged from the clinic? Just a minute. So we'll continue. So what is the expected waiting time until a patient is discharged from the clinic? So let me first write what are the arrival rate and service rate and customers. Okay. And so lambda is the arrival rate. So 60 patients per hour. So per hour 60 patients are arriving. So it is lambda. And the waiting room does not exceed, does not accommodate more than 14 patients. That means the system capacity is 14 plus 1 because the waiting room accommodate only 14 and one is getting serviced. So totally the system can manage 15 patients. And the traffic intensity is nothing but your lambda by mu. So lambda by mu is lambda is here 60. So 60 by 40. So it is 3 by 2. Okay, so in this scenario, let me go for the calculation of the first part. So the first part is determine the effective arrival rate of the clinic. Effective arrival rate of the clinic is nothing but a lambda dash, which is mu. Mu dash is equal to 1 minus P naught. So we have to calculate what is your P naught, and for P naught we have two formulas. One is when lambda is not equal to mu, one formula, and when lambda is equal to mu, we have one formula. But we here when the lambda is not equal to mu, this problem. So in this problem, lambda is not equal to mu. So we can go with the formula of P naught with lambda not equal to mu. So which is nothing but the lambda not equal to mu, your P naught is 1 minus lambda by mu upon 1 minus lambda by mu the whole power k plus 1. So 1 minus lambda by mu, 1 minus lambda by mu, the whole power k plus 1. If k is 15, 15 plus 1 is 16. So when you're just calculating this when using a calci, you can get it. It's 0.0007624. So this is the arrival that is rate. That is your arrival rate in the sense that your lambda dash is mu into 1 minus P naught. This is here a system is empty. P naught is 0.007624. We have to calculate their effective arrival rate, which is mu into 1 minus P naught, and mu is 40 here. 40 and 1 minus P naught. So here the effective arrival rate is 39.9695 per hour according to the system. So coming to the next question, what is the probability that the arriving patients will not wait? That means P naught. So already we calculate what is your P naught here. So P naught, the system is empty. If the system is empty, only the patients, whenever they are coming, they will be getting appointment with the doctor directly. They will be going and for the consultation, right? So the system is empty. P naught is equal to 0.00762. And what is the expected waiting time until a patient is discharged from the clinic? So discharged from the system, entire system, that is LS. So from the total LS system, it is so the formula you have, it is lambda by, you have lambda by mu minus lambda, and minus this is k plus 1 lambda by mu the whole power k plus 1 upon 1 minus lambda by mu the whole power k plus 1. So just substitute the values of lambda, mu and k here. So this is actually mu. So lambda 60, mu is 40 minus 60, k plus 1, 60 into 60 by 40 all power 16 upon 1 minus 60 upon 40 whole power 6. So when we calculate, it is going to be like 13 patients in the system. So L is in the system, and here what is asked, it is nothing but waiting time. So we are not going to calculate directly here waiting time of the system. So we're just going to find using here waiting time and average customers in the system. Based on that, we are just going to calculate this. So we are just going to use this formula to find a waiting time in the system, which is in the base of ls upon lambda dash, which is the effective arrival rate. So your ls already calculate the waiting, the average number of customers in the system is 13, and already effective arrival rate is calculated. So that using these two, we can find what is here WS. So WS is nothing but 0.3253 hours. So find actually for all those three questions we have showed you the values, right? So effective arrival rate is 39.9695 per hour, and no customer in the system, probability of no customer in the system is 0.007624, and waiting time of the system is nothing but 0.3253 hours. Coming to the second problem, at a railway station, only one train is handled at a time. The railway yard is sufficient only for two trains to wait, while other is given signal to leave the station. Trains arriving at the station at an arrival rate of 6 per hour, and the railway station can handle them on an average of 12 per hour. Assuming Poisson arrival and exponential service distribution, find the steady state probabilities for the number of trains in the system, and also find the average waiting time of a new train coming into the yard. If the handling rate is reduced to half, what is the effect of the above result? So we are just going to proceed with the given arrival rate and service rate initially. Then with finding with what is your LS and what is your WS, and finally they have given that reduce your yeah make the handling rate, that service rate, half, and find what is the effect of change in the result you had. Okay, so that's what is given in case 1 and case 2 here. So first let me go with the case 1. For that, your arrival rate is 6 here. So the yard is sufficient, only yeah, so only one train is handled at a time. So this is a single servo model. Railway yard is sufficient only for two trains. So two trains to wait. So one will be running. So obviously your K will be 3. And the train arrives at the station at an arrival rate of 6 per hour. So lambda is equal to 6. And it can handle them on an average of 12 per hour. So servicing rate is 12. So they are supposed to find with your steady state probability of the number of trains in the system. That means LS. So to calculate with your LS, we are supposed to need to go with your here formula LS is nothing but lambda by mu and so on, so right. So before that we'll go with finding what is your Pn, P naught. So P naught is 1 minus 6 by 12, and 1 minus 6 by 12 the whole power 4. So it is 0.533, and so we'll calculate with what is the your steady state probability for the number of trains in the system, right? So LS. So we'll to go for your LS, we'll go with the formula. Already we know it is lambda mu minus lambda, and minus of k plus 1 lambda by mu the whole power k plus 1 upon here 1 minus lambda by mu the whole power k plus 1. So substitute that here and we'll find it, and the effective arrival rate will be based on this is, it is mu into 1 minus P naught. So it is mu here, it is 12, and P naught is we calculated it is 0.533. So it is the effective arrival rate. This the calculation of effective arrival rate is needed because we are supposed to find here average waiting time. So initially you decide what are the things we want to find before proceeding. Okay. So we'll just proceed with the finding of here LS, yeah, before finding a WS, I am in need of LS and here arrival rate. So here LS is lambda by mu and this thing. So on substituting here lambda by mu everything here, we can get that the steady state probability for the number of trains in the system is 0.7333 trains. And the waiting time of the new train coming to the yard is, it is LS upon lambda dash. So LS we calculate, lambda is effective arrival rate is this thing. Okay. Similarly, we have to find the problem when the handling rate is reduced up. Already it is 12. So 12 upon 6 is, this is the scenario. Okay. And when I'm just looking at this case one where my lambda is not equal to mu. What about when my lambda is equal to mu, the formula changes. Here Pn will be in the case of 1 by k plus 1. Okay. Pn for varies from for all your n is equal to 0, 1, 2, 3, everything. Whereas here my P naught is the special formula. Then for your Pn it is lambda by mu the whole power n on P naught. Okay, based on this we'll calculate because here we have the capacity till 3, so we'll show it. It is P1, P2, P3 and P naught is equal to P1 is equal to P3 is equal to it's 1 by 4 0.25 and effective arrival rate is your mu is 6 and it is 4.5 per hour. So we know it is a mu into 1 minus P naught, right? So substitute this and you will get it. And LS is actually when mu is equal to lambda is equal to mu, your LS is k by 2, so it is 1.5 trains. And waiting time, we know it is again the LS by lambda dash. So when I'm just calculating waiting time, it is 0.0333 hours. Looking on the comparative of this thing, your waiting time is more than the double the average of your waiting time when mu is equal to 12. It is 0.333. It is double more than the double of your WS when mu is equal to 2. Okay. So coming to the next problem, a petrol pump with only one pump can accommodate 5 cars. The arrival of cars is Poisson with a mean rate of 10 per hour and the service rate is exponentially distributed with a mean of 2 minutes. How many cars are in the petrol pump on an average? What is the probability of a newly arriving customers finding the system full and leaving without availing the service? So accordingly, when I'm just going with the mean arrival rate is 10 per hour, so lambda is equal to 10 and the service time is with a mean of 2 minutes. Okay, so 2 minutes, so I have to convert as this is an hour, I have to convert this in the here in hours. So convert this into hours, so you'll get 30 per hour, right? Actually, we'll be taking as 1 by mu is equal to your scenario is like yeah. So 1 by mu is equal to 2. So we'll be converting into hours. So it is like 30. So your mu is equal to 30 hours. Okay. So in this, yeah, the system can accommodate 5 cars and your traffic intensity is lambda by mu. So lambda by mu, it is 1 by. And what is how many cars in the petrol pump on an average? So on an average, they are asking about LS. So you know the formula for LS is already the same thing. We'll be substituting and calculating it. What is this? On average, the petrol pump can have 0.492 cars. And what is the probability of a newly arriving customers finding the system full and leaving without availing the service? Because it can accommodate only 5 cars at the petrol pump, right? So when it comes more than 5, they have to leave, right? So it is the probability of 5 cars in the system, P5. So P5 is, yeah, we'll have it, this is P5. P5 is nothing but it is known as lambda by mu, the whole power 5 into P naught. So it is 10 by 3 power and this is P naught we calculated already, where here your mu is not equal to a lambda. So according to that formula, we got it, the system is full and it is 0.00274. Coming to the next problem. So, in one person, barber shop has 6 chairs to accommodate people waiting for a haircut. Assume that the customer who arrives when all the chairs are full leaving without entering the barber shop. Customers that arrives at an average of 3 per hour and spends an average of 15 minutes in the barber chair. So accordingly, a lambda is 3 or yeah, oh yeah, so 3 per hour, so 3. And here in the same scenario, and the average 15 minutes is mean the barber chair, so convert into hours, so it is mu is equal to 6. And calculate here the arrival is the customer who arrives when all the 6 chairs are full have to leave. So 6 waiting chair and 1 is in the service chair, so totally it is 7. And traffic intensity is 3 by 4. So what is the probability the customer can get directly into the barber chair means when the system is free, obviously you have to get into the chair, right? So it is directly a P naught. And what is the expected number of customers waiting for a haircut? So waiting for the expected number of customers waiting for the haircut. So you have to go for their waiting for a haircut is nothing but it's LQ, not the waiting time. Okay. How much time can a customer expect to spend in the barber shop? So in the whole system, what he has to whether if it is busy with the one person the service, other he has to wait. So then along total, you have to go with system waiting time. So what's the fraction of potential customers are turned away? So you have to calculate with when they'll be turning away. So it is nothing but we'll be calculating here Pn when n is equal to 7. So P naught is 1 minus lambda by mu, 1 minus lambda by mu the whole power, k plus 1. So it is P naught is calculated, which is actually the directly the customers coming to the shop and getting serviced. And arrival rate is mu into 1 minus P naught, which will be used for calculating a WS and everything. So here LS is nothing but using formula we'll calculate it, and we are supposed to find only the customers in the queue, so which is in terms of ls minus lambda dash by mu. So the system's custom expected number of customers waiting for the haircut is 1.3875. And coming to the next waiting time in the system is Ls upon lambda dash. So Ls is 2.11 and lambda dash is 2.89. So the waiting time in the system is 0.7301 hours. And what is the fraction of potential customers turned away? So it can accommodate turned away is if it is more than 7, it is turned away, right? So it is P7, 3 by 4 the whole power 7 into P naught. So P naught is already calculated. So 3.7 percentage of potential customers turned away. Okay. So with this, we'll go with the final lookup of the quick reference of the formulas. So P naught when lambda is not equal to mu is this thing. P naught when lambda is equal to mu is this thing. So similarly, when Pn lambda is not equal to mu is the formula, and lambda is equal to mu is equal. So when you're looking at this formula, P naught or Pn, when lambda is equal to mu, you have the same output, it is 1 by k plus 1. And lambda dash is mu into 1 minus P naught. And Ls is this thing. And based in Ls also we have two scenarios, when lambda is not equal to mu and when lambda is equal to mu. Based on Ls, we will be defining here LQ, Ls and WQ. Okay. So with this, we'll end this session. Thank you.